Hello everyone, welcome to Tech Talk Universe. Einstein's general theory of relativity has been confirmed again. Wait a second, isn't this something we already know about? Well, there are indeed some differences. This isn't the first time astronomers have observed gravitational waves from the collision of two black holes, but it is the first time they've found evidence of precession in their orbits. The precession rate is 10 billion times faster than the previous record holder. What is precession? It's a phenomenon that occurred in the black holes before they collided and merged. How did astronomers use gravitational waves to observe black holes? And why does this research combine the initial success of general relativity with its final prediction? Let's go back to Newton's time. According to Newton's law of universal gravitation, a binary star system consists of two celestial bodies that orbit around their common center of mass, attracted by each other's gravity. If no other celestial bodies are influencing the binary system, their orbits would form a fixed ellipse, making everything simple and beautiful. However, the reality isn't always that straightforward. As early as the mid-19th century, astronomers discovered that Mercury's orbit exhibited a phenomenon called orbital precession, where the long axis of its orbit rotated by 1.6 degrees every century. Precession refers to the phenomenon where a rotating object's axis of rotation revolves around another axis. It's similar to how the axis of a spinning top rotates. Initially, people thought that this precession was simply due to Mercury being influenced by other planets' gravity. However, no matter how carefully they calculated, astronomers found that Mercury's actual trajectory always deviated from their calculations. Every century, the precession of Mercury's orbit was 43 arcseconds, about 0.012 degrees, more than theoretical predictions. At the time, there were various explanations for the difference between the observed orbital precession and the theoretical predictions. Some astronomers believed that there must be an undiscovered celestial body located between Mercury and the Sun, which affected Mercury's orbit and caused the precession. This would be consistent with classical mechanics. They even gave this unknown celestial body a nickname, Vulcan. Others believed that there might be fundamental errors in Newton's theory of gravity, such as gravity not strictly decreasing with the square of the distance. However, neither explanation could perfectly account for the observed results. This issue remained unresolved until 1915, when Einstein's general theory of relativity emerged and provided an explanation. Using the general theory of relativity, Einstein discovered that the orbital potential energy of planets included an additional term inversely proportional to the cube of the distance from the Sun. After recalculating using the general theory of relativity, people found that this correction term perfectly accounted for the discrepancy between the theoretical predictions and the observed results. It explains Mercury's strange orbital behavior. The correction for Mercury's orbital precession became one of the most significant initial pieces of evidence for the general theory of relativity. Besides orbital precession, another significant prediction of the general theory of relativity is the existence of gravitational waves. When a binary system revolves around each other, it causes ripples in space-time. When these ripples pass through Earth, they cause the surrounding space-time structure to stretch and contract periodically. This is what we call gravitational waves. However, gravitational waves cause extremely tiny space-time fluctuations. Even when two black holes dozens of times the mass of the Sun collides, the resulting gravitational waves only cause length changes on the order of 10 to the power of -18 when passing through objects spanning kilometers. This is equivalent to just 1/1000th the size of an atomic nucleus. So, although gravitational waves were predicted to exist as early as 1916, it wasn't until the 21st century that scientists finally had the technology to detect them. That's why gravitational waves are often called Einstein's last prediction. How do physicists detect gravitational waves? Modern gravitational wave detectors typically consist of two vacuum tubes several kilometers long, arranged perpendicularly. At the intersection of the vacuum tubes, there are mirrors and a laser source. After passing through a beam splitter, part of the laser beam goes through, and part of it is reflected, creating two perpendicular beams that travel into the vacuum tubes. At the ends of the vacuum tubes, some mirrors reflect the laser beams to the intersection point. The beams then pass through the beam splitter again and reach a screen, forming an interference pattern. If the degree of space-time distortion changes, the interference pattern will also change because the two beams have traveled different path lengths. By observing the changes in the interference pattern, physicists can detect the existence of gravitational waves. Now we encounter another question. How can we use the signals from gravitational waves to study the celestial systems emitting these waves? Taking binary black holes as an example, when two black holes orbit each other, they emit gravitational waves. Like electromagnetic waves, gravitational waves carry energy. As a result, during the orbiting process, the black holes lose energy through the radiation of gravitational waves. Consequently, the black holes gradually get closer to each other, and their orbital speed increases until they eventually merge into a single celestial body. The strength, frequency, and shape of the gravitational waves emitted during this process depend on several physical parameters, such as the individual masses of the two black holes, their spins, the black hole's orbits, and the angle between the line of sight and the orbital plane. At this point, astronomers do two things. The first task is to process the signals received by the gravitational wave detectors through noise reduction, filtering, and normalization, among other techniques, to remove as much interference from non-celestial sources as possible. The second task is to define a range of parameters, and then use computer simulations to determine what the gravitational waves produced by the merging binary system would look like under those physical parameters. Next, astronomers compare the simulated gravitational waves with the observed signals. If they match, that's great news. If not, they will adjust the parameters and see if the signals simulated with the new parameters are closer to the observed results. By iterating this process, they can find the set of parameters that best match the observed results, which allows them to determine the physical characteristics of the gravitational wave source. Furthermore, this helps them identify the corresponding celestial objects responsible for the gravitational waves. On September 14, 2015, the gravitational wave detectors LIGO and Virgo made their first detection of gravitational wave signals from a binary black hole merger. The signal was designated GW150914, with the two letters GW being an abbreviation for gravitational wave in English. The following numbers represent the date the signal was detected. This detection occurred 100 years after the introduction of the general theory of relativity, finally confirming Einstein's last prediction that gravitational waves truly exist. A mere 2 years later, in 2017, the Nobel Prize in Physics was awarded to 3 representative scholars who made significant contributions to gravitational wave detection. It's worthwhile to note that Nobel Prize winners usually experience a long waiting period of several decades before their scientific achievements are recognized and withstand the test of time, leading to the award. Due to the strong gravitational field near black holes, astronomers in 2015 believed that one day they would be able to detect gravitational wave signals from binary black hole systems and observe the phenomenon of orbital precession as the black holes orbit each other. This expectation turned into a 7-year wait before the anticipated discovery was finally made. In October last year, a research team from Cardiff University made an exciting discovery after analyzing data for 2 years. They found evidence of binary black hole orbital precession in one of the gravitational wave signal sources, GW200129. This discovery effectively combined the initial success of general relativity with its last prediction. According to their analysis, the two black holes in GW200129 had masses 40 times and 23 times that of the Sun. The observed gravitational wave signal allowed scientists to simulate and recreate the corresponding celestial model. It revealed that the orbital precession frequency of the black holes was as high as 3 times per second. To give you an idea of how high this frequency is, let's compare it to the precession of Mercury mentioned earlier. Mercury's precession amplitude is 43 arcseconds, or about 0.012 degrees every 100 years. This means that it takes Mercury approximately 3 million years to complete one precession cycle. Before this discovery, the highest observed orbital precession frequency record was held by a binary pulsar system. However, even in that case, it took 75 years for the system to complete one precession cycle. Compared to the previous record holder, GW 200129 is nearly 10 billion times faster. Gravitational waves have emerged as a new field in astronomy in recent years, providing astronomers with a fresh window to observe the universe. Unlike traditional electromagnetic wave observations, gravitational waves barely interact with matter as they propagate. This means that they are not obstructed by interstellar gas and dust encountered along the way, allowing us to obtain information from even deeper regions of the universe. More importantly, astronomers can now combine information from both gravitational waves and electromagnetic waves to analyze the same celestial objects. This is similar to enjoying food by using both our senses of sight and taste simultaneously. By integrating information from different channels, astronomers can piece together a more complete and accurate picture of the objects being studied. Since the first detection of gravitational waves in 2015, scientists have not only analyzed observational data, but also continuously built new gravitational wave detectors and upgraded existing facilities to make them more sensitive, allowing them to detect even weaker gravitational waves. Currently, gravitational wave detection projects around the world have reached their third phase. Compared to the first phase, which detected only 3 events, and the second phase, which detected 8 events, the number of events detected in the third phase has increased significantly, like being on a rocket, reaching a total of 81 events. If it weren't for the COVID-19 pandemic forcing the detectors to temporarily halt operations, the third phase could have observed even more events. But don't worry. The fourth phase of the observation project has already returned in March this year, equipped with even more sensitive instruments. In the coming years, what surprises will gravitational waves bring? Let's look forward to it together. That's it for this episode. This is Tech Talk Universe. See you next time.